Hello everyone, this is Group 11. My name is Afolabi. My other team members are Rokiwa and Rotimi. Our project title is Network Denial of Service Detection. Whenever we are asked to explain what software-defined networking is, two things come to mind. First of which is the three-layer architecture as we see here: application layer, control layer, and data layer. The second thing that comes to mind is centralized intelligence. Therefore, software-defined networking is a network architecture approach which makes the network intelligent and centrally programmed with software application. The most important term to pay attention to in this definition is software. As we continue on this subject, it is important to take note of two key terms: data plane and control plane. In the data plane, everything that has to do with actual user traffic is addressed here. The data plane is tasked with processing and delivery of packets based on states in routers and endpoints, fast timescales per packet. In the control plane, it basically deals with communication between the software or hardware networking components. This establishes the state in routers to determine how and where packets are forwarded, slow timescales per control event. This flowchart summarizes what we aim to accomplish in this project. Incoming packet flow through switches. The POX controller, which collects stats and keeps dictionary of counts from the switches, collect the stats from the switches in timely manner. If the web stat from a particular host is greater than predefined threshold, then the flow rule is added automatically to deny the traffic. We have an established count that if it exceeds predefined threshold, then there is an update to the flow rule to deny traffic. This we will see shortly when we get into the demo part of this presentation.
Good afternoon, everyone. My name is Rotimi, and in this slide, we'll be discussing about DOS in action. I think it's important we first of all explain what DOS is. DOS means denial of service, and DOS is a type of attack in which the attacker sends an unusual high volume of traffic to its victim's machine. And it does this for one purpose. It does this in order to overwhelm the resources on that victim's machine so that that victim's machine won't be able to service other legitimate requests from other users. So that's what we are trying to simulate in this our demonstration. How an SDN infrastructure with a controller is able to detect a DOS attack and based on some scripts inject the necessary rules to deny the host performing this attack. So to simulate this, we would have to use web requests. So on H4 server, we would have the web service running. Then we simulate it so that one of the hosts, either host 1, 2, or 3, would send continuous web request to host 4 in order to simulate this attack. Then we see what happens. So in order to simulate this attack, it's very important we use Miminet because Miminet helps us or it provides us with a platform that gives us a realistic virtual network. If not for Miminet, in order to simulate this kind of attack, you probably would have to go and get physical computers or servers. You need to get open flow capable switches. You need to get a controller, either a hardware, you install the controller on it. I mean, you need to get a physical topology set up. But good, we have something like Mimnet. And what Mimnet does is it helps us to create this realistic virtual network that makes use of a real kernel that works in a controller. And also within this Miminet, we also have the switch or switches and application code. So you have all this within a single virtual machine. To simulate this attack, we would have to use or we have to create what we call a linear topology. And this means we are going to have two switches and four hosts. So the first switch will have three hosts connected to it, which are host 1 named H1, host 2 H2 as we can see in the diagram, and host 3 H3. Then on the other hand, we would have on the other end of the switch, which is switch 2, we would have our server there. And on this server, what we intend to do is to probably have a web service running, and we submit an attack, excuse me, an attack from switch 1. And lastly, we have to make use of POX, which is the SDN controller, which is what we are going to use to demonstrate this our project. So what's POX controller? So there are different types of controllers that could have been used for this project. So we have, for instance, Floodlight. Floodlight is a Java-based controller. We have POX, which we are making that is Python-based. It's open source, which is one of the reasons why we chose it, and it also comes pre-installed with Miminet, so it makes it very easy for us. Even though the one that is installed on Miminet is the one that runs by default on Miminet is not POX controller. It's the default controller. So to make use of POX controller, you would have to navigate to the right folder, enable the right custom modules. But I mean, POX controller we already have POX controller installed inside Miminet, which makes it very easy for us to use. Now, to simulate this particular attack, what we have to do is quite straightforward. After we have simulated that, what the POX controller does is quite straightforward and simple. I think Afolabi already mentioned it, but I will throw more light on it here. So the POX controller collects active flows from each of the open flow capable switches. And these flows are presented on a command line. So when my colleague Rukia is doing the demonstration, you would see all this in there. We also went further to ensure that we created a custom module. And so what this custom module does is it shows the flows that are added to the switch whenever any traffic is generated from any host to another host. So it gets a count of this traffic. And what POX controller does is it gets a count of this traffic. So it sends a request to the switch asking for this information. The switch responds with the required information, and based on this, POX controller continues to update its dictionary. Depending on based on the threshold we've already set, once any flow hits that particular threshold, any web request flow actually hits that particular threshold, the controller automatically sends or automatically generates a rule and adds it to the switch with a drop action, and this automatically drops that particular flow while allowing other flows to go through. My colleague Rokia will continue with the demonstration, which we will all see. Thank you.
Hi, this is Rukhaya. I'll be continuing from here. I'm going to talk about the simulation results of our project. To begin with, I'm going to start with the topology. To create the topology, we are using mn command with custom option to build the custom topology. The line in the script provides a hook to the mn command that allows it to be imported and the custom topology to be used. The multi-host.py file builds the custom topology with 4 hosts and 2 switches and a remote controller. Basically, Mininet comes with a built-in controller class to support several controllers, including the OpenFlow reference controller. But to run another controller like POX, one way is to start up the POX in another terminal window and then use -- controller with IP and the port details as shown in the command. To start the POX controller with the selected stock component, we are entering the following command on a terminal session connected to the Mininet VM. The stock component which is used here is forwarding.l2_learning. This component makes OpenFlow switches act as a type of L2 learning switch Although this component learns L2 addresses, the flow it installs are exact matches on as many fields as possible. For example, different TCP connections will result in different flows being installed. The option info.packet underscore dump, this simple component that dumps packet underscore info to the log, sort of like running TCP dump on a switch. The next option is samples.pretty underscore log. This simple module uses log.color and a custom log format to provide nice functional log output to the console. The next option, log.level. POX uses Python logging infrastructure. POX default level is info. To specify debug mode, we are using hyphen debug. In POX console, see the log shows the controller started and connected to the switches successfully. The custom module used here is flow starts. The file should be placed in the ext folder of the POX controller to be invoked. This Python module is used to collect web stats on the switches by the POX controller. The module collects both flow stats and port stats as shown in the figure. Let's generate some test traffic between hosts to see how POX build flows in the network. Run the mininet ping all command, which runs ping tests between each host in the emulated network. This generates traffic to the controller every time a switch receives a packet that has a destination MAC addresses that is not already in its flow table. You can see in the POX console window the log messages showing what is happening. When the POX controller running the forwarding.l2 underscore learning component receives a packet from a switch, it tells the switch to flood the ARP packet out its other ports to other switches or host. One host eventually responds to the ARP request, and then forwarding.l2 underscore learning component sends open flow messages to each switch to load the required flows into the switch flow tables. To see the contents of the flow tables on all switch, we are executing the mininet command dpctl dump flows as shown in the figure. To check ARP tables on each host, execute mininet ARP command. For example, to show ARP table for host h1, enter the following command h1 ARP. Let's start the HTTP server on a particular host of the topology. We are making use of h4, and the module which is used is simple HTTP server. To simulate the DOS attack, make continuous web requests from a particular host. In our example, we are making continuous requests from h1 to h4 using the command shown in the figure. The web requests are done in the for loop of about 15 times. Per the custom POX component created flowstats.py, the web requests on switches are counted, and the threshold 5 requests are set up in the code. So automatically a flow rule will be added on the switch to block the web request for this particular host if the request count crosses the threshold. We can verify the same rule using the command dpctl dump flows. A flow with the action drop will be added. The custom module flowstarts.py has actually blocked the host 10001 because the web requests cross the threshold limit of 5, which is hard coded in the code. And we can also see from the port stats the rx underscore dropped count has been increased to 1. We can clearly see a flow rule has been added to block traffic from h1 to h4, which is on the port 80, and the action drop has been added because the web request made by h1 was greater than the threshold specified in the custom module flow stats, and whereas the other hosts are able to make the get request without any problem.